up guys? Today we'll be learning about IEEE 754. So the example that we'll be looking at is taken from assignment 3, problem 5. So the first problem wants to know what is the equivalent value as a decimal number. So when you're given a long number like this, you want to break it up into 3 different parts. So the first part you want to break it up into is the first bit. And then you take the next 8 bits, and then you take the next 23 bits. And those are your 3 different parts. The first part is your sign, the next 8 parts is your exponent, and the rest of the 23 bits, that's your mantissa. So for our sign is 0, which means our number is going to be positive. If the sign was 1, you would know that your number is negative. The second part is the exponent. So our exponent is 100000110, and you want to convert that from binary to decimal. And the way you do that is you see how many spots this is. So this is the 0 spot, this is a 1, this is a 2, and you follow that all the way up, and this will be the 7th. So when you're calculating this number out, you simply just do 2 to the 1 plus 2 to the 2 plus 2 to the 7th. And as we can see, our exponent will be 134. Well, when you're dealing with single precision floating point, you get that exponent and you subtract a magic number to it. And our magic number is 127. So we're going to do 134 minus 127, and that makes our exponent 7. So the next part is our mantissa. The thing with the mantissa is everything after the mantissa is followed by 1 point whatever this is. So for example, this is our number we're getting for the mantissa, and we're just going to start it off with 1.10101, and we don't really need to follow up the rest of the zeros. So to convert this part, all we have to do is we count again, but we start from a different number, and we're going to start from here. This is going to be our -1, this will be -2, and this will be -3, this will be -4, and this one will be -5. So we just add up all of our 1s. And as you can see, we're going to have 1 plus, because of this part right here, 2 to the -1 plus 2 to the -3 plus 2 to the -5. And if you put that in your calculator, you add all that up, you'll get 1.65625. But that's not our final answer. You get your mantissa and you multiply it by 2 to the exponent. And our exponent is 7. So we're going to do times 2 to the -7, or times 2 to the 7th, and we're going to get 212. And that is our final answer. So this number, the equivalent decimal number, is 212. So part 2 wants us to represent the following numbers in the IEEE 754 32-bit floating point notation, written as binary. So the first number is 125.015625. So the first thing you want to do in this problem is you want to take the number on the left of the decimal point. So in this case, 125. And this part's easy. You just convert this over from decimal to binary. So the way to do this, there are many different ways to do it. You can take 64 plus 32 plus 16 plus 8 plus 4 plus 1, and that equals 125. And then you just convert that over to 64 is 2 to the 6th, 32 is 2 to the 5th, and so on. And you can find that is going to be 1111101, and then dot. You don't know what the right side is. The right side is 0.01562.5. So now we have to convert this decimal part into binary. So to do this, we're going to have to work with the table. So this is how this table works. You get your decimal, which is 0.01562.5, and what you're going to do is you're going to multiply it by 2. So everything in this column, you take what you got in the first column and you multiply it by 2. So when you multiply that by 2, we get 0.03125. And this last column, you always put the number in front of the decimal. So in this case, our number is 0, so 0 goes here. And then we take everything on the right of the decimal and we put it back into this new column. So then our new row starts 0.03125, and we multiply that by 2, and we get 0.0625. And we still have a 0 on the left of the decimal, so we're going to put a 0 here. Then do what we've been doing. The 0.625 goes down here. Multiply that by 2. We're going to get 0.125. There's still a 0 right there, so it goes 0 here. Same thing, 0.125 times 2 equals 0.25. The 0 goes there. The 0.25 goes down here. 0.25 times 2 is 0.50. The 0 from here goes right there. The 0.50 goes down here. 0.50 times 2 is 1.0. And now we have a 1 on the left of the decimal. So the 1 goes right here. And this 0 goes down here. Then we have 0 times 2 equals 0. The 0 goes here. And that's when we know we stop. So now you want to look at this far right column, right? So you read these numbers going down. So now our number is going to be our 125, which is this number, and we're going to read these numbers down. So that's going to give us 0.0000010. So we know our sign right here is going to be 0 because it's a positive number. Our exponent is going to be 127 plus 6. And the way we get 6 is we look at this number. So this number, in order to get it in our mantissa form, which is 1 dot, etc., we're going to have to move this over by 1, 2, 3, 4, 5, 6. So that's where we get the exponent 127 plus 6. And 127 plus 6 is 133, so this is 133 in binary. And lastly, our mantissa is just everything else. So it is all of this. And so you fill all this up, and then you just fill out zeros the rest of the way. So that's pretty much our number. That's going to be our final result with our sign right here, our exponent. So let's see, our sign right here, our exponent over here, and our mantissa the rest of the way. And you just follow it up with zeros. So that's part 2-1. Part 2-2, we have another number, 263.3, and we do this the exact same way. So the first step again is you do 263 and you turn that into binary. So 263 is that in binary, and you don't know the right side because it's that 0.3 value, right? So again, we make our chart, and this chart's a little different. So let's just do it the same way we've been doing it. So we do 0.3 times 2 is 0.6. This is a 0 on the left of the decimal, so it's going to go 0 right here. This 0.6 comes back down. 0.6 times 2 is 1.2. The 1 goes into the third column. The 0.2 goes in the first column. 0.2 times 2 is 0.4. The 0 goes in here, 0.4 goes down here. 0.4 times 2 is 0.8. 0 there, 0.8 there. 0.8 times 2 is 1.6. 1 here, 0.6 there. 0.6 times 2 equals 1.2. 1 goes here, 0.2 goes there. 0.2 times 2 is 0.4. 0 goes here. And then, as you can see, you got somewhat of a pattern. You see, in this row, you have your 1.2. In this row, you're going to have your 1.2. So you can kind of see that this answer is just going to keep repeating. So this part is going to end up repeating again. 1.2, 0.4, 0.1.6. And then, as you can see, it goes 1.2, 0.4. And you can assume it's going to go 0.8, 1.6, and keep repeating. So this problem's a little different. You still read it down, so let's just continue doing how we're supposed to do it. So we're going to do our 263 dot, read it down. So we're going to do our 0, 1, 0, 0, 1, but you know this value is just going to keep repeating. So we put the repeating symbol on top. And then we do everything else the same way. So our sign's going to be 0. Our exponent is going to be 8. And you can see that by doing 1, 2, 3, 4, 5, 6, 7, 8 to get the 1 dot. 1 and some change. And you add it to that magic number 127. So 127 plus 8 is, this is 135 in binary. And then next part you do the mantissa. So the mantissa is just all of this. But in that last problem, whenever you filled in the rest by zeros, this one just keeps repeating. So there aren't going to be filling in zeros. You're just going to be filling in this 1, 0, 0, 1. So our final result is going to look like this. We're going to have our 0 for our sign. Our exponent's going to be 135, which is this in binary. And our mantissa is going to be 0, 0, 0, 0, 0, 1, 1. And then it just keeps repeating with this 1, 0, 0, 1. So as you can see, it's 1, 0, 0, 1. It just keeps repeating. 1, 0, 0, 1, 1, 0, 0, 1. And that's how you do 2.2. Okay, so question 3 asks, order the following floating point numbers in increasing value from 1 to 4, where 1 is the smallest number and 4 is the largest number. So there's a trick in doing a problem like this. You don't actually have to convert every number. You can just compare numbers. So for example, the first thing you want to do is look at the sign bits, right? So there's only one number that's a 1, and 1 is negative. So you already know right off the bat that this 1 is going to give you the most negative value. So that's the first one. That's going to be the smallest number. Then you look at the exponent. And you can already tell that this fourth number has the largest exponent. So you already know that that's going to be the largest number. These two numbers have the same exponent. So you already know that this one is going to be 4. Because of that exponent, that's going to be 4. So now you're just between these two numbers. So these two numbers have the same exponent, so you go to the mantissa. If you look at the mantissa right here, you can already tell that this number is going to be bigger than this number because this significant bit is bigger than this. So therefore, you're going to get this number. This top number is going to be larger. And you can see that that's going to be the next largest, and that's going to be smaller. So that's the answer for number 3. Part 4 asks, give value of the smallest number which satisfies the two requirements. So part A says the number is strictly larger than 1, and B says a number can be represented exactly in IEEE 754 format. So let's look at part A. It says a number is strictly larger than 1. So 1 in IEEE 754 is this, right? So if you want a number strictly larger than 1, the only difference is you're going to have this 1 at the end. So this is pretty much going to be 1 with just a little small number added to it. So the way we calculate this is we're going to do 1 plus 2 to the negative 23, because that's what this is right here, times 2 to the 0, because this exponent is 127. So 127 minus 127 is 0, so that's our exponent, and this is the answer you're going to get. A really small number plus 1. So number 5 asks, an IEEE single precision floating point which is greater, the number of representable numbers between 1 and 2 inclusive, the number of representable numbers between 2 and 3 inclusive, or they are the same. The answer is A, the number of representable numbers between 1 and 2 inclusive. And this is because if you're looking at 2 and 3, both of those numbers require 2 bits. And that means that you can be more accurate with numbers between 1 and 2 in IEEE 754 format than 2 and 3, because 1 only requires 1 bit. In general, the more negative a number is, the larger amount of representable numbers there are. So the closer you are to 0, the more representable numbers there are. And if you're looking at a range with a negative number, that range will probably be bigger. So part 6. What is the smallest positive number you can represent in the IEEE 754 double precision format? Represent this number in scientific notation. So in double precision format, instead of having 20 or 32 bits, it goes up to 64. So the smallest positive number will be zeros all the way up, and there's a 1 at the end. And in IEEE 754 double precision format, instead of minus 127, you subtract 1023. So in this case, the exponent is negative 1023. So we're going to have 2 to the negative 1023 times 2 to the negative 52, because this is the very last bit. And that's going to be this answer. So this is the smallest positive number in double precision format. And lastly, number 7. What does the following bit pattern represent, assuming that it is one of the following? A single precision IEEE 754 floating point number, and a MIPS instruction. So just like how we've been doing for IEEE 754 format, you look at the exponent. So these bits right here, 1, 2, 3, 4, 5, 6, 7, 8. And if you convert that to decimal, that will be 120. You subtract your 127, and you're going to get your negative 7. And for the rest, you're going to do 1 plus, and then this Manteesa part. So as you can see, this is negative 1, negative 2, negative 3. This will be negative 4, negative 4, and this will be negative 5, negative 6, negative 7, negative 8, and negative 9. So as you can see, we added that negative 4, negative 7, and negative 9, and you add that to plus 1. So that will equal 8.37 times 10 to the negative third. So that's part A. Part B is just you want it as a MIPS instruction, so you can look in your notes. This is what I got.